Cambridge Muslim College, training the next generation of Muslim thinkers.
Here we see the domain field on the left-hand side, and then on the right you see something called a quantum cloud. Now, this was inspired by Basil Hiley, who's a friend of David Bohm, both quantum physicists, and the idea he was trying to capture was the internal space of a human being, and then try to project this internal space out to the outwards towards the rest of space. Now, the point behind this is that there is something about this work of art that explains artistically the basis of the models that arise from quantum field theory for consciousness, believe it or not. So I'll come on to that shortly. But moving on to the main subject, we here see a list of some of the major models for consciousness, some of which we've discussed in depth today, for instance, integrated information and so forth. But there are many others. And one of the things we find in some of these models is that they are not all entirely reductionist. In other words, you don't start from the elementary constituents and work up, but some of them are actually, in fact, top down. So we need to look at higher order objects and collections of information on objects to determine information from the system. Just generally, if we could look back a bit to Erwin Schrödinger, who we always associated with quantum theory, you'll be surprised to know that actually he was very interested in this field, and he wrote a series, gave a series of lectures in 1943 in Dublin, and they were called the What is Life lecture collection. And he asked a very, very important question, which is really what I'm trying to get at, which is just by considering the elementary constituents, in other words, molecular elements of a biological system, can we therefore, from those small elementary constituents, build up a picture that describes an entire biological system? Can we work out, for instance, how a liver works just by looking at, carbon atoms? And he noticed that there was something called a definite high degree of efficiency of biological structures and functional stability. And crucially, the only way to describe these things from a classical perspective was a statistical approach. In other words, we can't look at large order collections. We've discussed it. Basil Alto mentioned something about statistics. There aren't that many elements that make up, so many atoms that make up biological structures. So in order to describe any sort of collective behavior, we use a statistical approach. He said that the statistical approach was only giving order in the average, and it wasn't enough. So this has been alluded to by Angelo Bassi, a physicist from Trieste, who takes it the next level further. He says, regarding brain function and consciousness, he feels that we need to think of a definition of consciousness and brain function, which boils down to configurations of particles in the brain. So this isn't the first time such things have been discussed. For instance, Descartes in 1641 actually spoke of memories being textured like patterns interwoven into the brain, and somehow the pineal gland, which is in the center, somehow would survey these patterns and then read them, and that would be how consciousness worked. Okay, that's not what we believe today, but there is something important about this analogy that we can draw from this regarding the patterns. So getting back down to brass tacks, where we start from is here. 1942, Lashley had studied memory, and he produced a very well-known result called the mass action hypothesis, which describes how memory works, but I'm not going into detail regarding that. The point here is he noticed that nerve impulses are transmitted from cell to cell, that's nerve to nerve, through definite intercellular connections. But all behavior seems to be determined by masses of excitation without regard to particular nerve cells. So what do I mean by this? Just to visually give you an illustration in case you're falling asleep. Okay, you see here, this is actually a real computer reconstruction of brain activity. I want you just to have a look at it, because we've been talking a lot, but actually this is the sort of thing we're seeing actually happening in the brain. And if you notice here, sometimes large areas of the brain light up simultaneously. The problem with this is it doesn't seem to follow any specific pattern, not an obvious pattern. So have we actually got it wrong? So far we followed what's called the neuronal doctrine. Neuroscientists and all scientists, neuroengineers and so forth, we've looked at nerve pathways following neurons. But should we be looking at something called the neuropil? Now, neuropil actually was a term, this phrase, the neuropil doctrine, was coined by Henry Stapp only last year in a conference in Arizona on consciousness. And he was referring to something that Walter Freeman, a neuroscientist, and Giuseppe Vitiello were talking about, which is the entire cerebral cortex of a mammal is covered not only in brain cells, but supportive cells, the glial cells and so forth, blood vessels and other tissue. And the point is that it's around about 1 to 3 millimeters thick, and nerve conduction can occur through that in the sense of not nerve to nerve conduction, but electrical conduction can occur through it. So the structure of the neuropil topologically is something like this. You have per hemisphere, we have a 1 meter squared surface, which essentially can be considered from a physics point of view as a two-dimensional surface with about 10 to the 10 neurons and 10 to the 14 synapses, colossal number of synapses and neurons in each hemisphere, but we can regard it as a two-dimensional surface. And the point, the crucial observations are, when we look experimentally, we do see coordinated oscillations in the brain and on the neuropil, but the crucial observation is the appearance of these. Now, when you observe them, they look like they're multiple spatial patterns resembling cinematographic film frames on multiple screens. And the sources of these patterns are the neuropil. So electrical activity from this two-dimensional perspective is in fact very much like a cinematographic film frame. And this isn't. This is a universal finding. And the crucial point is that there's not only this type of frame activity, but there's instant resynchronization of vast numbers of neurons over a large, in terms of neurons, very large range, long distance communication. So here's now, hopefully, a picture, an illustration from a mouse brain. On the left here, you see the very fast moving frame type things I'm referring to. And in the middle, you see a time smoothed image of this, where just to give you an idea of what's happening at a more gentle pace. On the right, not so interested in that's the brain blood flow. But if you look at this here, the vital clue is that the activity that you're seeing, the appearance, resembles something like phase transition. So when you have water vapor and it condenses, it forms this sort of fog type substrate. And this is the sort of thing that we're looking at. So if we try to describe this using classical physics through the brain, we run into great difficulty. And the reason is that long-range diffusion, chemical diffusion is very slow, and extracellular dendritic currents that run across are actually weak. And the crucial thing is that neurons are actually tiny compared to the distances we're talking about. What we're observing is long-range correlation, so classical physics doesn't really work. It's not compatible with this. Then in 1967, which is the actual first time this observation was studied by physicists, Umezawa and Ricciardi analyzed this and noticed a similarity between this and a phenomenon that we see in condensed matter physics, which I'll explain in a minute briefly. But we're seeing ordered patterns here maintained by long-range correlations mediated by something which are called massless quanta, which I'll explain, because we always think of quanta as only being a single particle, but in this type of physics it can be collections of objects, which is why it's called many-body physics. So they produced a very important seminal paper. This paper, heavily understated, and it's really the basis of all quantum field theory models of the brain, called Brain and the Physics of Many-Body Problems, 1967. And they hypothesized there must be some quantum dynamic underlying the brain's macroscopic phenomenology. Now, we're not talking about collapse of wave functions, things. This model has no care for collapsing the wave function. It doesn't need to do that. If it does it, great. Well, if it doesn't matter. But there's still a quantum phenomenon underlying it. And this has been, has been developed tremendously by Freeman and Vitello into what's called the dissipative quantum field model. So just to fill in those who maybe not be physicists here, what type of physics we're talking about is this. In crystals, we see elastic waves which propagate through the crystal. And the reason that actually crystals form crystal structures, with from an atomic scale, it's like me standing here and another bunch of people standing all in line, lining up in perfect harmony. The massless quanta that causes this correlation is called a phonon, and it's elastic wave. In a ferromagnet, the magnet, the small things line up because of a massless quanta called a magnon. And in superconductors, which is a very remarkable thing in physics, we see something called Cooper pairs arising, which cause this. Okay, there's no point teaching this in detail, but if we just look at another visual analogy, this is actually, which might surprise you, it's actually a school of fish. But I just want, whoops, sorry, going back again. Why is it not allowing me to do that? There we go. I'll let it play. I was trying to skip it forward, but if we wait for about 15 seconds, you'll see what I'm talking about. We've all seen schools of fish, but I want you to just observe this behavior, just to give you a visual analogy, what I mean by long-range correlation. Okay, this is an analogy, a very good visual analogy, but if we watch now, they seem to be swimming together, and eventually you'll see them behaving like they all know where they're going all the time as one big collective. So here we go. Okay, there we are. Now what's that? And this sort of behavior. It's a good visual analogy because it shows what I'm trying to get at. And when a large collection of objects behave like they're one object, we call that a massless quanta. It has a name in physics. It's called a Nambo-Goldstone boson. But the mechanism in the brain obviously isn't fish. We shouldn't have fish in our brain, but we do have a lot of water. About 80% of the water by weight and 90% by number of molecules is actually water. There are obviously many other molecules, but it's an important molecule because it has something called an electric dipole. In other words, there's a charge, a positive and negative end to a water molecule. So effectively, it looks like a little, a positive end and negative end. It's got a pair of them actually, but you see it has a symmetry around its axis, what's called mathematically called an SU2 symmetry, and that symmetry is important because if we have water molecules floating around or almost lined up, if we then introduce something that disturbs that symmetry and breaks it, then we have a very important result, which I'm going to explain, which causes these large collections to form all lined up in perfect harmony. This operates down at the micro level, right down at the nano level rather, at the level of microfilaments and microtubules, which I don't have a picture of, but you can trust me, it's right down at the very basic level. So, well, the mechanism, this is the mechanism. We have an external stimulus entering the brain, then this causes a spontaneous breakdown of the rotational symmetry of the water molecule dipole. In other words, it disturbs the symmetry. And here, the most crucial result is the Goldstone theorem here. Now, the Goldstone theorem in physics is something that's used in high energy physics. It's used in particle physics. It's what the things like the Higgs mechanism depends on. It's fundamental. It basically says when there's a breaking of the symmetry of something, an upsetting of the symmetry, what happens is you get a long-range correlation, a large collection of things working together as if they're one, a collective mode. And they're called Nambo-Goldstone bosons. So think of them as the collection of fish we've just seen, all acting in harmony. Well, then just to give you, this is a little bit more technical, just for those who are a little bit more mathematically knowledgeable, not too much detail, just a bit more detail, especially for physicists. But the overall formalism, how do we make this work? Well, it's based upon forming memories. The Namber-Goldstone bosons, which are the collective modes, represent memories, and these will represent patterns on the brain. So the quantum field formalism is that the brain is an open system coupled to the environment, hence my picture of the environment and the human internal space by Anthony Gormley. And what happens is the brain is represented by an infinite number of damped harmonic oscillators. Essentially, you model it as a quantum, by quantum field theory, we represent the collective modes by A sub k, where K is a generic label denoting degrees of freedom like spatial momentum, and we denote the number. We call the number of modes for all K the memory code, and that is that's the code that is we associate with the memory, and the state of the system in that memories with a memory code of NA is 0 sub n in brackets like that. So that's because we call it the lowest energy state, we call it the vacuum state as well. There are lots of names for the same thing. The crucial result mathematically from the mathematical physics point of view is this lemma by Kelligini et al., which says that to set up what's called, from the physics point of view, a canonical formalism for such a dissipative system, it requires that we need to double the degrees of freedom. We introduce a time reverse copies of these modes. We call them tilde modes, and therefore the environment is like a time reverse image of the actual main system, in this case the brain. The next important result, that the energy, because it's a dissipative system, the energy fluxes from heat exchange of the system and environment interface are balanced. So we have the important result that for all these modes, if you have a common frequency here, omega sub k, the total energy is 0, so we can extract this result here, that the number of modes, both internally in the brain, is equal to the mirror modes, or the tilde modes externally. So what we're saying is that we could actually define a vacuum state, the collective mode, as being one for which the difference between this difference is 0. So given any other n prime, if we find it satisfies the same relationship, we can call it a vacuum state. So the long and short of it is that there are an infinite number, therefore, of ground states or vacuum states, and each representing a different code. And so we associate these codes with memories. So the next final technical result, which I'll just point out, it's very important, is that Vitiello, is that we can, in the infinite volume limit in such a system, there is no unitary transformation that maps a vacuum state of one code n to one of a distinct code n prime. So that basically means that there's no, these memory states cannot mix with each other. There's no interference. So the physical interpretation is that there are infinite numbers of memory states, each with its corresponding code. The memories can coexist without any destructive interference, and they can be accessible sequentially in the recording process, and the corresponding memories are different and distinguishable. So n is a good code, and then so therefore we see the brain as a collection of a large sort of superposition, not the same superposition as in quantum theory, but the sort of large collection of these memory states for all n. Okay, that's all. That's how the actual memory states are set up. But how does this relate to consciousness? And the way it relates to consciousness is that the mirror modes, which again going back to the Anthony Gormley picture there, you see the tilde modes are like self-interactions. And responsible in the Vitiello model for conscious processes and self-awareness. And therefore consciousness actually emerges as a manifestation of the dissipative dynamics of the brain. And then there are another major conjecture regarding this, another possibility for how consciousness arises, is that these what we call dipole wave quanta, these collective modes, just as though you may think they're just an imaginary thing, they behave like particles and they can interact, and so they can interact with photons, for instance, electromagnetic photons. So therefore, if they do that in the submicroscopic system of the brain, down at the protein level, down to the protein filament levels and microtubules, the Gibbon-Yasu conjecture is actually the dynamics. They haven't a mechanism that's as clear as Freeman and Vitiello, but that's the mechanism. So I'm nearly at the punchline, but before I get to the punchline, I just want to point out, so what's the point of this model? Is it just a pretty bunch of maths muddled with neuroscience? The point is, before the main punchline, the point is that it does accurately predict the macroscopic brain phenomenology. It not only produces a prediction for the rapid cinematographic film frames. I'm not going to show the proof of these results, but it has been confirmed. It also accounts for the very low energy required to excite the sort of patterns that occur in the brain. It actually produces much more than that. It produces information about phase modulation and a conical phase modulation which occurs, and with apexes, what are called null spikes, that trigger off these patterns. And they always occur between frames and on frames, and they even go as far as predicting that there are inverted cones for information perception and intentional action. You'll find conic upright cones, and these things have been confirmed experimentally. So the overall summary of the experimental evidence is that it does actually account for the observed dynamical formation of spatially extended domains of neuronal synchronized oscillation and their rapid sequencing. That's what it does. But I just want to point out something here, really very important. Now, we can work away with differential equations and matrices using neuronal networks. In other words, consider the brain as a bunch of wires all connected up in a large, complex connection. But there is no conventional neural network that adequately models or simulates these observations, and that's really a remarkable result experimentally. But now for what I regard as the punchline, which is the last paper published by Freeman before he passed away last year, along with Vitiello, is this one, which they've published in a paper called Mind and Matter Entangled in EEG Amplitude Modulation, and it's double. Now, what they found was that mental percepts that we see were correlated to the electrical structures that were generated by this mechanism. And so there was a correspondence to briefly existing neuropil structures and forms with co-occurring brief mental experiences or percepts. The crucial thing is they were not correlated to the external stimulus. So in other words, if I show you a cheese sandwich, it's not going to show the same pattern every time you see a cheese sandwich, but it's going to correlate to how you felt like when you were eating it, or where you were sitting, or what you were doing at the time. In other words, what you were experiencing in relation to it. And the other point is that the brain is actually remembers meanings rather than memories. The memories are actually there, but they correlate. It seems to work by meaning. So the patterns are correlated to experiences and perceptions that you associate with those external stimuli. And therefore they proposed that there was actually no way of distinguishing whether it was mind, or whatever mind is, from matter. So in fact, Vitiello says that he tries to interpret this as the mind, or as the external thing, as the tilde modes, and that in fact that we are in a conscious sense in an inseparable double. In other words, we have a physical side and a essentially exact sort of replica in addition to that, which is somehow, call it whatever you will, side. And another aspect of us, which is married up in these tilde modes. So in other words, so we have in fact got just to point out, this is a quantum field model. The sort of physics that's involved in this is the same physics, or very, very similar physics, that we use in high energy physics, we use to find using particle physics and so forth, which is remarkable. So, but the crucial thing is that quantum fields we've spoken about and heard about today. When, for instance, Adam Barrett was talking about electromagnetic fields, that is a quantum field. And when we're saying the electrical activity of the brain might be responsible for consciousness, what we're saying is essentially the same thing. But quantum fields can be different. They can represent, for instance, one particle. In this case, this quantum field is generated by the electrical activity of the brain because of the electric dipole of water, but it's actually still an electric field of sorts. But quantum fields need not be that. There are other possible quantum fields. And so have we possibly found a model that may somehow, if we could perhaps in this case look at the vacuum states that we looked at, the memory states, could we find a way of integrating them? Could it actually fit with other ideas from physics, other ideas from physical models of consciousness? Can we even find a way of introducing quantum computation into this model? And if, as Kobe Kremnitz has said, we do have this pleasant surprise that phi does end up collapsing psi, could we even have a completely unified model for consciousness? And we may be close to finding a physical formulation for the biggest mystery of all time, our consciousness. But even if it doesn't collapse the wave function, it doesn't matter, because it doesn't really require it. We don't need to know whether it does or not, because this physical mechanism in itself is quite remarkable, and it would be a triumph if we could prove it to be true. Now, one more point is that integrated information has something very beautiful about it, that the perceptions, how I felt when I had a cup of tea and a jam donut the other day, what color, how I feel when I have the color of the color red or purple. These things, these qualia, have a multi-dimensional representation in what's called a qualia space. So you can find a sort of a geometric structure, a topological structure for these in what's called qualia space. And would it not be very nice if we could actually find some sort of correlation between neuropil forms or structures that we see electrically from those findings of the quantum field model and the geometry of qualia space? Okay, it's a long shot, but it may be useful, maybe worth considering. It's definitely quite an exciting phenomenon. So I'm going to just move to sort of my conclusion and just sum up, really. And going back to the picture, and this isn't an actual picture of the sculpture by Anthony Gormley near the O2. And so I just want to say, to sum up, that it does actually definitely appear that we need to consider more than just biological machinery alone in understanding consciousness. And after centuries of looking purely at anatomical and biological structures, we're now, as scientists, examining phenomena that are essentially not actually visible to the naked eye, nor immediately form part of the cellular substrate of functioning biological material. Phenomena that traditionally belong to the realm of theoretical physics. After all, a field is something you can't normally see. So it is increasingly apparent that deeper physical mechanisms are at play. Clearly, it appears that quantum phenomena need to be studied more closely in this context. So what can we say about the substrate of consciousness itself? No one has an answer yet, of course, but as perhaps I'm going back to Adam Barrett again, has suggested, perhaps it's a fundamental property of fields, maybe fundamental fields. And it's worth pointing out that we should all be disappointed to learn that what we learned at school was wrong. That in fact the most fundamental, and we've talked about particles just now, the most fundamental object in the physical world is not considered to be a particle at all. All particles are just manifestations of fields, and there are technically no particles, only fields. So should it not then make sense that somehow that the consciousness itself may arise as a property of these fields? It certainly makes more sense. And it could be that perhaps we are in fact therefore even more intimately a part of the fabric of the physical world and nature, not just at a biological level, but at a much deeper physical level. Perhaps the full implications of what we've heard throughout the day today have not really sunk in. There's a lot to consider. But by reflecting, I think, on these ideas and these proposals very carefully, what we're actually saying, possibly, is that consciousness itself may well be a fundamental physical property and a physical phenomenon, even possibly more fundamental than just what we are experiencing at the biological level. And we've spoken of panpsychism and so forth earlier today as well. So this outcome itself, that it's a physical phenomenon, could well be revolutionary. It could even be the biggest paradigm shift we have ever experienced.
Cambridge Muslim College, training the next generation of Muslim thinkers.